Hi everyone, I'm Stephanie Peart, and welcome to the Salt-Tea Podcast. So I'm super excited about this week's podcast because we finally arrived at density. And density is a super important concept when it comes to the ocean because it's what drives the motion of the ocean and impacts stratification and creates barriers between surface and deep layers and plays a role in where and how organisms live and how they get their food supply. And for also so many other reasons. So let's dive in. Okay, so in this episode, we are going to be putting together our knowledge of salinity and temperature in order to discuss ocean density. So if you're a brand new listener, first, welcome, and two, hit pause. Hit pause on this episode and go back and listen to episodes 1 through 6 so you can really enjoy this episode. Go ahead, hit pause, I'll wait. Welcome back! If you're listening to my voice now, I'm assuming you went back and listened to episodes 1 through 6. Or, okay, if you just kept listening, then I know you are so excited about this episode that you just couldn't wait to get started talking about ocean density. And so I will just say you can always go back and listen to episodes 1 through 6 and then this episode again for maximum oceany goodness. Alright, so at this point you know that I like definitions, and in science it is always important to define your terms. So let's start out by asking the question, what is density? Well, when I go to dictionary.com, I find 8 different definitions for density. So again, if you learn only this one thing, always define your terms. For instance, one of the definitions for density is stupidity, slow-wittedness, obtuseness. And of course, this is not the definition that we'll be using in this episode, but could you imagine if someone only knew about this one definition and then they were listening to this episode? It would just totally not make any type of sense when I say something like density drives the motion of the ocean, or what they'd really be hearing is stupidity drives the motion of the ocean. And oi, that just would get so confusing so fast. So 1, always define your terms. And 2, in this episode as well as in future episodes, we'll be using the physics definition of density as the mass of an object divided by its volume, or mass per volume. And here's a simple way of thinking about it, especially when we start talking about the density of water and seawater. Imagine for a moment a box, a nice square or rectangular box. In your imagination, the box could be either a small box like a shoebox, or a larger box like a packing box, or even a larger box like the box your refrigerator or other large appliances came in. But whatever size you're imagining, just make sure to keep the same sized box throughout this entire exercise. So you have your box. Me personally, I'm imagining a large square packing box about 3.3 feet or a meter on each side, so that I have a nice big box that will have a volume of about a cubic meter. So now, regardless of how big your box is, imagine you fill that box with just a few packing peanuts or foam peanuts. And sorry, I don't know what they're called in other countries, so I'll include a picture on the Salty Science Weebly slideshow page. Okay, so now you've added your peanuts. Now imagine you're picking up your box. It feels pretty light, right? And if you were to weigh your box, now with just a few packing peanuts, it would still be pretty light. Now, imagine that you fill your box with peanuts. And again, now imagine that you pick up the box. Does it feel any heavier? Well, packing peanuts are pretty light, but you should notice that the box feels a little bit heavier. Now imagine that you still have a few more packing peanuts that you want to fit into the box. So you cram them down and squish the packing peanuts together so that you get the last of the packing peanuts into the box. Now how much does your box weigh? So okay, maybe cramming a few extra packing peanuts into a box wouldn't change the weight of the box too much, but if you had a very powerful scale or balance, you would notice that the weight of the box increased in weight as you added more packing peanuts. Now here's a fun side fact. Weight and mass are similar but different. When you step on the bathroom scale in the morning, you are actually measuring your weight, which is highly impacted by gravity, or the force of the earth pulling you down. So if you imagine someone like, say, Bill Nye, the science guy, because honestly he would do an experiment like this if he could. Let's say Bill Nye, the science guy, steps on his bathroom scale one morning, and let's say his bathroom scale says he weighs 180 pounds. Okay, quick disclaimer, I don't don't really know how much Bill Nye the Science Guy weighs, but we're just gonna imagine he weighs 180 pounds here on Earth for this exercise. Okay, so now Bill Nye, being Bill Nye, who has great connections to state-of-the-art technology, and let's say he's able to teleport or to travel very quickly to Mars with his bathroom scale. Well, now when he steps on his bathroom scale, assuming that it's only been a few minutes since he stepped on the scale on Earth and he didn't eat a large meal during his interplanetary travels, his bathroom scale would say, instead of 180 pounds, it would say he only weighed 68.4 pounds. And similarly, if he were to travel quickly to Jupiter and stand on his bathroom scale again, it would say that he weighed 421.2 pounds. So you can see that in one morning, Bill Nye or you and me could be 3 very different weights depending on which planet we're standing on. And even on our own planet Earth, there are slight variations in the gravitational pull because Earth is not perfectly spherical or uniformly dense. For instance, if you want to lose weight really quickly, just go to the top of Mount Everest. You'll drop weight in no time. Okay, so this is one of the reasons why scientists prefer to reference the mass of an object rather than its weight, because mass is a measure of how much matter an object has. So Bill Nye, assuming that he didn't have a large breakfast between his interplanetary transportation, would have the same mass on Earth, Mars, and Jupiter, and any other planet he traveled to, even though his bathroom scale said his weight changed. And even though there are slight variation in Earth's gravitational pull or acceleration depending on your location, for the most part, we know that it's on average roughly about 9.8 meters second squared. So we can use this knowledge to calculate the mass of an object, even if all we know is its weight, which mass equals the weight of an object divided by the gravitational acceleration. But if you're measuring weight in pounds, you have to do some conversions. So a super easy way to convert to mass is to simply convert to kilograms, which then you just have to remember the number 2.2. Take the weight in pounds and divide it by 2.2 to get kilograms. So for instance, Bill Nye in our example weighs 180 pounds. 180 divided by 2.2, if we were to round up, is 82 kilograms. So the mass of Bill Nye is 82 kilograms, and he'll be 82 kilograms on Earth, the Moon, Mercury, Venus, Mars, and all the other different planets. Okay, so now going back to our box scenario, mass is defined as the amount of matter or stuff or substance an object has. So if our box only has a few packing peanuts, it has less quote-unquote stuff, versus if we were to fill it, then it would have more stuff. And then again, if we were to even cram packing peanuts inside our box, we'd have even more stuff in the same volume. That is to say, the same sized box. Okay, so now this is where we bring it to density. Density, which we use the Greek letter rho to symbolize, is defined as the amount of mass in a given volume. So your volume is whatever size box you're imagining right now. Me, I'm imagining a box 1 meter by 1 meter by 1 meter. So a box with a very nice volume of 1 cubic meter. Now if you divide the mass of the box, mass being the amount of matter, or the weight of your box divided by 2.2, and then divide that number by the volume of the box, you'd get your density. So for instance, if I know that my box full of packing peanuts weighs, say, 1 pound, 1 divided by 2.2 is 0.45, so its mass is 0.45 kilograms. Now divide that by the volume of my box, which is 1 cubic meter. So the density of my whole package is 0.45 kilogram per cubic meter. And if I were to have fewer peanuts in my box, the density would be less. And if I crammed and squeezed as many peanuts as I could into the box, the density would be higher. And that's kind of another way that you can look at density. How much matter or stuff is squeezed into a specific volume. And what's nice about density is that it, for the most part, stays the same. For example, if I had 3 boxes filled with the same amount of packing peanuts, the density would be roughly the same, even though the weight or the total mass of 3 boxes is more than just 1 box. And what if I were to add marbles to my box full of packing peanuts? How would that change the density of my package or box? That's right, the volume isn't changing, but the weight or the mass would be changing. So by adding more stuff to my box, the mass is increasing, therefore my density also has to increase. Alright, so now let's start talking about the ocean. So now imagine that the packing peanuts are water molecules. The same concept applies. The more water molecules you have in a set volume, the higher the density. So now there is a reason why I chose the cubic meter sized box, and that's because when it comes to water molecules, pure water has a density of 1,000 kilograms per cubic meter. Pretty easy to remember, right? And so if I were to add salt to this volume of water, or like when I was adding marbles to my box full of peanuts, the salts are going to increase the density of the water. And the more salt there is, the higher the density. And so the global ocean, on average, has a salinity or concentration of salts of about 35, or 35 grams of salt per kilogram of water. And so the average density of seawater is about 1,030 grams per cubic meter at the same temperature. I said temperature. And why would I say temperature? Because just like salinity, temperature plays a huge role in density, especially the density of water. And remember that temperature in science, as well as in this podcast, is a measure of how fast the molecules are moving. The faster molecules move or vibrate, the higher the temperature and the warmer the object feels. The slower the molecules move or vibrate, the lower the temperature and the cooler it feels. And absolute zero or 0 Kelvin is the point or temperature when all molecules stop moving. So water molecules in the liquid state are constantly moving around. And even so I wouldn't necessarily be able to see it with my own eyes, they are in fact moving all around inside my box. And the faster the molecules move, the more they like to expand out. So in the case of my box full of packing peanuts, if I put my very full box of packing peanuts on a surface that was vibrating or shaking, say the back of a truck driving down a very bumpy road, the peanuts would start to move and naturally some of them would start to fall out of the box, especially if I left the box open. And therefore the density of the package, if I don't put the peanuts back in, would also be impacted. And another way of thinking about it, if you had a group of people together on a really hot day or just in a really hot room, are they going to want to stand super close together or would they just naturally spread apart? Well, if it was me and there was a whole lot of sweaty people around and I'm sweaty, I definitely wouldn't want to be standing too close to anyone, even if they're my best friends. Or imagine if you're in a room full of people that want to start doing jumping jacks. What would they have to do? They would have to spread out to give each other room. So water molecules are similar in that as you add heat energy to the water molecules start to move faster and want to spread apart, but your box or your container remains the same size or volume. So if you scoop up a liter of warm water, you technically have fewer molecules than if you scoop up a liter of cooler water. And this is also why if you've ever had a bottle full of water and then left it in your car on a really hot day, when you come back, the container looks swollen, and that's because the water molecules wanted to spread out, but they couldn't really because they're trapped and therefore could only push on the walls of its container. And similarly, if you remove heat from the water molecules slow down and are able to come closer together, and you can fit more water molecules in the same size container. And again, you can think of it as if you had a room full of people, some people would have to leave the room if everyone wanted to start doing jumping jacks. But when they stopped doing jumping jacks, you would be able to fit more people in that same room. So just remember, cold equals condensing or moving closer together, and hot means spreading out. Okay, so just to say it again, fresh water has an average density of about 1,000 kilograms per cubic meter. And I didn't say this before, but I'll say it now, at 4 degrees Celsius. And if we were to add a bunch of salt to this water, what would happen? That's right, the density would go up. But we could bring the density back down by increasing the water's temperature. And so as you can see, temperature and salinity play a major role in water density, and the relationship is not linear. And so what that means is that we can have the same density with different combinations of temperature and salinity. And so in marine science, some great scientists developed what we call a temperature salinity diagram, or a TS diagram, that relates density to salinity and temperature. And I have a great image of this, so I'll be posting it on the Salty Science Weebly page under the slideshow tab. But wait, this is not the full story. We haven't talked about pressure yet. Pressure also plays a huge role in density. So let's go quickly back to our box and packing peanuts. So you have your box full of packing peanuts, but now imagine you place something really heavy on top of them. Say a bunch of textbooks you have just lying around the house, or phone books. Do people still use phone books? Anyway, so you place something really heavy on top of the peanuts. What's going to happen? Well, some might get pushed out of the way, but all of the peanuts directly under the books will get smushed. But in the case of the ocean, it's not books smashing water molecules down, but actually other water molecules. And if you've ever tried to lift or carry a bucket of water, as you keep adding water to the bucket's going to get heavy really fast. So if you've ever gone scuba diving or snorkeling or just dove down to the bottom of a deep swimming pool, you've noticed that you feel a lot of pressure. And that pressure is actually coming from the weight or mass of the water molecules above and all around you. And fun but very important side fact, the relationship between depth and pressure are related so well that in marine science, we'll often just measure pressure, which then will tell us our depth. So for example, 10 meters deep is equivalent to about 10 newtons per square meter, which is super useful information. Okay, so when you have this pressure squeezing molecules together, it does two things. One, it's forcing molecules closer together, so it's increasing density, because if you took your box down to the bottom of the ocean, you'd end up having more water molecules in your box. And two, like I mentioned in the last episode, adding pressure to a system also adds heat, which also impacts density. So now, just like with temperature, where we have potential versus in situ temperature, we also have potential and in situ density because of pressure. So just as a reminder, in situ temperature is the temperature we would have if we lowered a thermometer or a thermistor to a specific depth. Or it would be the temperature if we were scuba diving and we measured the temperature with a thermometer while we were at a very deep depth. Now, if we were to bottle some of that water at that deep depth and put a thermometer in it so we could read the temperature while we slowly resurfaced, we would notice that the water would actually start to get colder. And this is because of expansion. As you bring the water further and further up, the pressure gets less and less, which allows the water molecules to expand. And when it does this, it loses heat, which, as you can imagine, will also impact its density. So scientists take this expansion into account by calculating potential temperature and potential density. And potential temperature is the temperature of a water parcel, which, FYI, we refer to a container's worth of water as a parcel. So potential temperature is the temperature that a parcel of water would have if it were raised adiabatically from some depth to the sea surface without changing its salinity. And adiabatically is a fancy word which means that we don't allow the water as it comes up to the surface to exchange heat with its surroundings. Or in other words, we take out any added heat due to pressure. And similarly, we do this with density. And there's a great table from Open University that shows the differences between salinity, in situ and potential temperature, as well as in situ and potential density, that I'll also be posting on the Salty Science Weebly page. Okay, so the last thing that I want to do in this episode is to mention sigma and sigma T. Sigma and sigma T is a type of shorthand we use in marine science because we know that the density of freshwater is 1,000 kilograms per cubic meter, and seawater, which increases the mass of water by about 2 to 3%, which then means that generally our density of seawater is somewhere between 1,020 to 1,030 kilograms per cubic meter. So to make our lives easier, we simply subtract 1,000 from the value to get a sigma value of 20 to 30 for seawater. And if we're not taking into account any pressure, which in special cases we don't have to, like when we're comparing water from similar pressures, we drop the pressure term. And when we do, we refer to that as sigma T. And actually in my own research, I often use sigma T values when looking for pycnoclines in estuaries. And a pycnocline is similar to a thermocline in that it's a section of the water column where density rapidly increases in a small change of depth. Okay, so now just to review everything we've covered. 1, density is a measure of mass per volume. And if you just remember one thing from this episode, this is it. Cold, salty water is more dense than warm, less salty water. And the density of seawater is a function of temperature, salinity, and pressure. As temperature decreases and salinity and pressure increase, density also increases. But as temperature increases and salinity and pressure decrease, density also decreases. And I also introduced you to the words and terms such as potential and in situ density, as well as adiabatic, sigma, sigma t, and pycnocline. Okay, so now it's time for one of my favorite parts. I get to tell you why we marine scientists care. So like I said in the beginning of this episode, density plays a super important role in the motion of the ocean. While the surface of the ocean moves mostly due to winds, the deeper ocean moves due to the density differences, and these density differences drive vertical movements of the water, because denser water is heavier than less dense water, and so it'll actually sink. And I'll be getting into this concept more when we talk about ocean circulation and the Great Ocean Conveyor Belt and many other fun marine science topics. Okay, and density also is super important because when you have less dense water on the top and denser water on the bottom, it actually creates a type of barrier. And this setup of barriers we often refer to as stratification. And the barriers can be good as it helps to keep phytoplankton up near the surface water so that they can get more sunlight for photosynthesis. But it can also be bad because while it keeps the phytoplankton up in the surface water, it can keep their nutrients that they need to grow in the bottom layers. As well as it can also prevent oxygen from mixing deeper down so that the denser water can actually end up going anoxic or depleted of oxygen. And as a fun aside, in 2018, the movie The Meg with Jason Statham contributed a thermocline, or really I would argue that it was a pycnocline barrier. But anyway, it was this type of barrier that kept the prehistoric megalodon in deeper water away from all humans. Until of course we humans broke the barrier, thus releasing all mayhem on happy-go-lucky vacationers spending their holiday at the beach. Alright, so now it's your turn to share. What are some other reasons we might need to know or want to know about the density and density differences of the ocean? And I know that all my listeners are super smart, so I'm looking forward to hearing what you come up with. And you can email me your answers at saltysciencepodcast@gmail.com. And our first listeners episode will air Friday, November 1st. And so if you email me your answers before then, you might just hear me read them out loud, or if you send me an audio clip of your answer, you just might hear your own voice on air. Won't that be exciting? Oh, and some more exciting news. I've posted some fun DIY experiments on the Salty Science Weebly page that goes along really well with this concept of density. And if you sign up and join the Salty Science crew on the Salty Science Patreon page, you'll have exclusive access to the videos of me and some special guests trying these experiments ourselves. Okay, so until next week, don't forget to reduce, reuse, recycle, and refuse, and to always stay salty. Thank you for listening to Salt-Tea Science. But guess what? You don't have to let the fun end here. Go to www.saltysciencepodcast.weebly.com, where I've posted some cool videos, my study notes, and some really neat experiments that you can try at home. And if you want to follow along with my own research, you can follow me on Instagram. User handle Teps Adventure. That's TEPS Adventure. All Salty Science episodes are available on iTunes, Spotify, Google Podcast, and YouTube, plus a number of other podcasting apps. If you like the show, please rate, review, and subscribe on iTunes, as this is the best way to spread the word about this podcast. Salty Science is listener supported, so if you would like to show your support, visit our Patreon page at www.patreon.com/Salty Science, where you can either make a one-time donation of any amount or join the Salty Science crew for as little as $1 a month. So visit the Salty Science Patreon and sign up today.